The goal here is to look for the critical points, the max, in this case the max and mins of this function f of x. So our first step is to take the derivative of this, and it's going to get a little messy real quick. So we say f prime x. We're going to start with our power rule, so we're going to multiply by our exponent 2/3. Okay, we're going to leave the inside of this function alone. And then we have to subtract 1 from our exponent, so 2/3 minus 1. 2/3 minus 3/3 is negative 1/3. Okay. We're not done yet because we have to multiply by the inside. This is a chain rule problem. The derivative of x squared minus 4 is 2x. So we can say f prime x equals, okay, 2 times 2x is 4x over 3. And because we have an x squared minus 4 to a negative 1/3, we can drop that down to our denominator and make it a positive 1/3. So x squared minus 4 to the positive 1/3. So there's our f prime. Now, the first thing we want to do is look for where f prime is 0. So we know that x equals 0 is going to be a critical point because that's where our derivative is 0. But the thing is, we also have to look for where our derivative is undefined. So you see there's some x values that could make the bottom equal to 0, which isn't going to be a slope of 0, but it's going to be an undefined slope, and that could be a critical point as well. So what we do is we set our denominator equal to 0 and our numerator, which we already did. We got x equals 0. Okay, so all right, well, the inside of that is going to be x minus 2 times x plus 2. And all of that is raised to the 1/3. It's equal to 0. Okay, so then we say x equals 2 and x equals negative 2. So we're going to make our table now with our value that made the numerator 0 and also our values that made the denominator 0. So we have our interval from negative infinity until negative 2, negative 2 until 0, 0 until 2, and then 2 until infinity. Okay, let's box this off. Okay. All right, and then we have f prime, and then we have f. What we've done in the past to determine if the derivative is positive or negative is we talked about the end behavior of the derivative, but now we have this crazy rational function, so that's not going to work. So instead what we have to do is we have to go into our interval from negative infinity to negative 2. We have to pick a number, plug it into f prime, and see if we're going to be positive or negative. So for example, negative 3 is in our interval. So think about it. Think about what the top and the bottom are going to be. The top is going to be negative 12, so we're for sure going to have a negative in the numerator. You can make that red, negative. Okay, in the denominator, we're going to have negative 3 squared is positive 9, and 9 minus 4 is going to be positive, and the cube root of a positive is positive, and we're going to multiply by positive 3. Overall, the denominator is positive. So we have a negative divided by a positive, which is going to be a negative. Okay, and if it's negative, that means that f of x is decreasing. So now we have to think about our next interval, and it turns out that the sign's going to change, and it's because what we have here is when we cross negative 2, this factor is going to change signs, but everything else, all the other factors are going to have the same sign, so it causes the overall output to change signs. But we can also just plug in like negative 1, a number in our interval again, and we can see easily the top's going to be negative again. And then on bottom, though, when we do negative 1 squared, that's going to be positive 1. 1 minus 4 is going to be negative. So then now, all of a sudden, the bottom is negative and the top is negative, so that ends up making the whole thing positive. So that means f of x is now increasing on this interval. Okay. Similar reasoning, it's going to switch back to negative on 0 to 2. And again, if you're uncomfortable with that, you could test another point, but it's going to give us the same idea. Because now that we're from 0 to 2, the numerator is positive, the denominator is still going to be negative. Overall, that makes it negative. So then we're decreasing again. And then when we hit 2, when we hit 2 to infinity, well, now we're going to go back positive, because now both the numerator and the denominator are going to be positive. So we go negative, positive, decreasing, increasing, decreasing, increasing. So what do we have then? Right here, we have a minimum at x equals negative 2. Right? I'm not going to write the full statement out. I'll just say our mins, that's at x equals negative 2. And then we also have a min at x equals positive 2. And then our max, our singular max happens when we go from increasing to decreasing, which happens at x equals 0. So if you look back onto the Desmos activity, it'll show you what this graph looks like. So basically, at the place where the place where the slope is undefined is where you have the points, like the two pointy parts. We can't define our slope there, but we can still recognize those as being minimums because they're local minimums on our graph. So look back at the Desmos activity, check out the graph, and you can make the connection between the max and mins we found here and where they show up on the graph.